Let me now explain how we can use MLE to estimate the scale parameter of exponential distribution. Assume that a data set x1, x2 up to xn follows an exponential distribution with scale parameter lambda. The objective of MLE is to estimate the value of lambda that maximizes the likelihood of the data, which is x1, x2 up to xn. The likelihood of observing the data from an exponential distribution is given by the joint probability as given in this equation. So, the likelihood function is the joint probability of x1, x2 up to xn, which is lambda e raised to minus lambda x1 times lambda e raised to minus lambda x2, so on up to lambda e raised to minus lambda xn, which is same as lambda to the power n times e raised to minus lambda I equal to 1 to n xi. So, that is the likelihood function, which is same as the joint probability of observing the data x1, x2 up to xn. And here the probability density function follows a exponential distribution. In this equation, we assume that the events x1, x2 are independent. The objective of the MLE is to find the lambda that will maximize the likelihood function given in this equation. To find the optimal value of lambda, we must take the derivative of the likelihood function in this equation and equate that to 0. However, the derivative of this equation is mathematically intractable. Thus, we take log likelihood function instead of likelihood function as shown in this equation. So, the log likelihood function is nothing but n times log natural of lambda minus lambda times summation I equal to 1 to n xi. When we take the derivative of the log likelihood function, we will get the value as n over lambda minus summation I equal to 1 to n xi. Equating this equation to 0 and rearranging, we get the lambda star, which is the optimal value of lambda, as n over summation I equal to 1 to n xi, which is same as 1 over x bar, where x bar is the mean value of those values.